Alright gang, MATH6500, very likely the last video in lesson 3, I believe is where we are. And I'll just be completely transparent with you. I'm probably not the best person to teach this section. This section is going to be on transformations. I'm not a huge fan of transformations. I think it's really interesting from a mathematical statistical perspective. But from an applied perspective, I always search for other options. And I'll try to explain that, the reasons, as I go through this instructional videos. So anyway, over on the right, you can, again, split screen, get some notes over here, and then we'll bounce this off some examples in R. So if the error terms are reasonably normally distributed and the error terms are close to having constant variance, then you may consider a transformation. Again, in the spirit of being completely open, honest, and transparent here, I'll always be honest with you, but I may not always be transparent about what's going on behind the scenes. There's a data set that we have. It's called ACT nonlinear, and I wanted to demonstrate this video using that data set. I used all of these transformations. I used transformations on X. I used transformations on Y. I used every combination I could think of on transformations on X and Y, and I could never get a model that was appropriate for being described with a linear relationship. So we have to take these to heart. I think it was, the error terms were reasonably normally distributed, but the error variance across each level of X was not close to having constant variance. So anyway, I'm going to introduce some new stuff in this video, along with trying to just give you just a very brief introduction to transformation. So what I've done here is I've laid out some prototypes. If we get a nonlinear function or relationship between X and Y that looks like any of these three, a go-to that you may consider would be 1 and 2. So 1 and 2 would be log base 10 transformation or a square root function. If you get something like this, you may consider the squared or the exp of X, which is just taking X raised to the base E. And then 5, 6, 7, the 1 over X, the exp negative X, and of course natural log of X. If you run into something like that, you may consider one of those three. It's more of a guide, not a rule, but I think it is helpful in determining which transformation that you may consider. All right, so where do we go from here? I tell you what, let's. I have a data set that will be available to you in the data folder. It's called nonlinear. So let's just go ahead and fit a model. I'll tell you what, let's go ahead and look at the relationship between X and Y using a scatter plot, which I would do a lot. And you can see just from the eyeball test that it doesn't appear that a linear relationship is appropriate for describing this relationship between X and Y, right? Again, we can't say, well, there's no relationship, because there is a relationship. We could use a nonlinear model to describe the relationship, but right now our focus is on linear models. So I would probably want to go ahead and just look at the model, even though I'm not at all hopeful of getting a very effective model, linear model. Now, for those of you who are p-value searchers, this is where, or p-value hunters, this is where things can get problematic. We have X is statistically significant as a predictor at the 0.01 level. We can look at the multiple R squared, which would be appropriate with one predictor. we can see the 57.1% of the variance in y is explained by the regression on x. Yet, when we dive into the assumption of normality, and I want to show you something new here. I'm not sure why I skipped over this, but previously, but if you're watching all the videos like you're supposed to and required to, it doesn't really matter because you're going to get this now. There's something called the, I'll tell you what, let me back up a little bit. Let's access the library car, and there's a really cool QQ plot function that I can do with what I call this model. Yeah. And I really like this better than the demonstration I've done previously with QQ plot because it gives you gives you the bands, and if all of the points fall within the band, then it's reasonable to assume that the normality assumption of our residuals of our errors is satisfied. Another thing we may take a look at is the Anderson-Darling test. So I'm going to type that out. So Anderson-Darling test. The Anderson-Darling test is super easy to carry out in R. First thing we have to do, we have to access the library, and I believe it's NOR-test. Yes, okay. And then we just do the AD test of our residuals for the model that we just created. Now this is really cool because it gives us a p-value, which kind of gives us a procedure using the kind of line in the sand, the 0.05 threshold, right? So the null hypothesis here is that the residuals, the errors, are normally distributed. So you can see since our p-value is greater than 0.05, we would fail to reject the null, indicating that we have normality of error terms. We can assume normality of error terms. However, and this is a huge however, when we start to examine the relationship between the fitted, I'll tell you what, let me, I would much rather do this. I like having the horizontal line there. When I examined the residuals over the fitted values, again, this should kind of look like a shotgun blast. It looks like anything but a shotgun blast. In fact, if you have a shotgun that's shooting this pattern, I don't think I'd want to shoot it because I don't think it'd be safe. All right, so we clearly have an issue here with modeling this relationship of these generic x's and y's that I created, modeling this with a linear function. So let's take a look. If we bounce back over to the right, we can see that the general shape of the scatter plot between x and y looked something like this. My go-to is always the natural log function. So I'm going to just call this a new x, and I'm going to just work with the natural log. Now remember, log of x, although we're used to it being ln of x, in R, the natural log of x is just uses the command log of x. All right, so I have new values of x, and now I'm going to look at the plot. I'll tell you what, let's create the model first. So I want my y as predicted by these new x's. And let's look at a summary. Oops. All right, well, that's kind of cool that we have this. Now, you can see, again, if you're a p-value searcher, statistical significance at the 0.01 level, and here we have statistical significance at the 0.001 level. I think the most important information that we can see from this output is that the multiple r squared is 57.1%, And when we implement the transformation, we about 99% of the variation in y is explained by the regression on this new x. Now, let's look at the plot between the new x and y, and let's include the ab line. And you can see we get an impressive, again, I want to hesitate to teach it that way. There's nothing really grand about the linear model. Other models are perfectly fine. But if our focus is on using a linear model to describe the relationship between these two variables, then this transformation lands us in the linear model being appropriate to describe this relationship. We can also look at the fitted values for model 2 over the residuals, model 2, or I should say the residuals over the fitted. And I'll tell you what, let me be consistent here. And you can see that we do have a relatively constant variance, kind of, again, a shotgun blast as a way of visualizing it. Now, sometimes we get into where we need transformations on y. And, you know, in case transformations on y are needed, a few that you may consider, and these go with the kind of the prototypes of transformations on y that you may consider. And again, you may need a transformation on y, you may need a transformation on x, and you may need a transformation on x and y. Now, I said earlier that I ran into a situation, or I believe I told you this, that the ACT nonlinear that I intended to use for this demonstration, I tried everything I could. I tried every transformation on x, every transformation on y, every combination of transformation on x and transformation on y, and I never could get a linear model to fit that data. And again, I believe it's because the constant variance assumption was so violated that I just couldn't get that. Now, what would I do in that case if I had that model? And if you remember, I was using ACT to predict first-year college GPA. Well, I would just completely scratch out the linear, simple linear regression or multiple regression models. I would dichotomize the dependent variable. First-year GPA, I would maybe dichotomize that from 2.0 and higher and 1.9 and lower, or maybe even 3.0 and higher and 2.9 and lower. So I would dichotomize the dependent variable, jump into or transition into the logistic regression techniques. So that would be my solution. I don't like transformations as much because I find that the interpretations, the predictions are a little clumsy, which I'm going to demonstrate for you in just a second. So, that would be my solution. Again, rewinding here and being slightly too repetitive, I may not be the best person to teach transformations because I'm not a fan. But let's say that we did want to stick with this transformation, this natural log of x transformation, and we wanted to predict y when x is equal to 500, for example. Now we have an issue here because we're not dealing in a model where we're dealing with x's. We're now in a model where we're dealing with the natural log of x. So the very first thing that I would want to do here is I'd want to take, let's just do predict 500. Let's just call it that. So I would want to convert the 500 to, it's always so tempting for me to do ln. So I'm going to convert the 500 using the log function for obvious reasons, because that's a transformation that we have. So predict 500, so 6.215. Now, next thing I would do is I would, this is going to be kind of good review from MATH6500 and earlier in 6500. I would create a new data frame, and I would have my new x, I believe is what I called it, right? Yeah, equal to the log of 500. And I would use the predict feature of the predict code in R. So I need my model name, which is model 2. And I'm going to use new data from the data frame that I just created. And I want to use the interval predict. All right, so for a x value of 500, we would predict, well, because, okay, first of all, the fit would be 0.354, but the 95% confidence interval would be run from 0.30 to 0.41. Okay, so you know, again, the prediction of a new value is requires another step, but again, you know, this is the way we would work this. Now, let's say we want to start with an x and increase the x, you know, whatever, twofold. And we're interested in, so this is starting completely new stuff. We're interested in the how the prediction will actually be carried out. So if we think about it this way, if we think about looking at the mean of y given the natural log of x, we would find this by taking our model and then we want to take a look at what happens if we increase this twofold. Now, if we want to look at the difference, right, the increase, it would make sense to me that we would take mu sub y given the natural log of 2x minus the mean of y given the natural log of x, which of course is going to be equal to this minus this. Excuse me for being lazy, but this is all going to be pretty easy to do arithmetically in our head. So we want to take this minus all this. Well, we can see the b0 minus b0 leaves 0. And the other thing we have is we have b1 times the natural log of 2x minus b1 times the natural log of x. We can easily factor out the b1, leaving us with the natural log of 2x. You probably see already where this is headed. So we're going to have b1. So we know the property of natural logs that when we subtract, we can rewrite that by dividing. Of course, the x's can cancel. So we can take b1 times the natural log of 2 to actually look at the increase in our x twofold. So in other words, if we're going from x to, from 1 to 20, we can look at the prediction increase by just taking the value for b1, which in this case was negative 0.079227 times the natural log of 2. Very easy to make that So we would expect a decrease, and that should be pretty obvious from the scatter plot that we created earlier, because we have a decreasing pattern of about 0.055, let's call it. All right, gang, that's about all I have. Yeah, you know, transformations I mean, they can be very cool, very interesting, and I believe I could teach an entire class on transformation, but we have bigger and better fish to fry than this. So anyway, I thought before you leave 6500, I'd like for you to at least be introduced to the process, the procedure for transformations, which you now have been. So, and also a couple things that I threw at you in this that's kind of new. Make sure you put in your notes about the Anderson-Darling test. It's very, very, very helpful. And I think the QQ plot that I used here, I kind of prefer, because it gives us those confidence bands. And if all of our points fall in those confidence bands, then you can almost be guaranteed that your Anderson-Darling normality test will be not significant. All right, gang, all I got. Take care.